can you hear me? Just put something in the chat, please. You can hear me? If you can hear, okay. You should hear me fine now. Brilliant. So, okay, not too many people today. That's fine. So, today I'm going to go through some problems on gravity, and just to show like how fascinating this topic is, because I always find it fascinating. And okay, so I really hope I will manage to share some of the excitement with you. Just before we start, just get rid of everything that we don't need. Okay, and shut down Telegram. It's always fair. People always start texting when I'm in the middle of doing something. Okay. How are you finding the physics assignment, the gravity assignment? 10 being incredibly difficult and 1 being super easy. Could you give me a vote, please? How are you finding it overall? 3 out of 10, 4 out of 10. Okay, so 3 means relatively not difficult. Okay, the last question is quite tough, but it's the last question. 3. Anyone else? There's 14 of you. Don't be shy. The question was, how are you finding the assignment, the difficulty? 10 being very difficult and 1 being not difficult at all. Okay, 4 people replied. Guys, I kind of want not attempted yet. Okay, you can put 0 if not attempted. 0 if you haven't attempted it yet. Okay, that makes sense. That's fine. Okay, so the problems are going to be similar, some of them very similar, and one of them I think accidentally gone through one of the problems, but not quite. Scale the other way. Scale is the other way around. Because, well, Judah, most people who have replied, they have been here last year, and they are they're quite trained. So don't feel bad. You'll get there. It just takes some time. Right. So, and so I'm going to share my screen. So do ask me a lot of questions, Judah. You have this wonderful opportunity. Okay, you should be seeing my screen now. If not, let me know. Okay. And the first question. So I've left the question. I've left the details out of questions, and I've done it. I've done it on purpose. Like draw a graph of G of R and U and R for the Earth. Like you might ask, what is that? Well, G is the gravitational field. Gravitational field. G is the gravitational field. Gravitational field. And U is the gravitational potential. Now, normally, we use V for potential, but in this in this assignment we use V for potential energy, so just be wary. Sometimes V is potential, sometimes V is potential energy. So just watch carefully. It should always be stated what V is, or it should be very obvious what V is. Okay. So for the Earth, well, we know the gravitational field of a point mass, and we know that outside the planet, the gravitational field is the same as if it was a point mass. So basically what I mean is that the Earth, this is the Earth, and let's say you are here, a distance r from the Earth, the Earth of mass m. And also imagine a different galaxy where instead of a mass, you have a black hole, so a point object of the same mass m. And if you're standing r meters away from the black hole, you would not be able by any means, by measuring the gravitational field, you would not be able by any means telling what is that? Is that a planet or a black hole of the same mass? So the size of the planet does not matter. The field is the same from a planet and a point object. Okay, if you're outside the planet, obviously. And that gravitational field, we know it's the well, let's say your mass is m, and the gravitational force to experience, is g, mass of the planet, mass of you, divided by r squared. And g, by definition, g is force per mass. So it's the force experienced by you divided by your mass. And if you divide this by mass, you get gm m over r squared. That's the expression for gravitational field outside the planet. So that's fine. So let's start with the gravitational field. And this is r. This is the distance from the center of the Earth. And this is the gravitational field. And we know that starting from the surface of the planet, r, it behaves, it is equal to g m divided by r squared. So it's inverse square relationship, 1 over r squared. I can keep it this way. So it's proportional to 1 over r squared. So the further you are, the smaller the g. Now, what the question is, what happens here? What is that? And here, the Gauss's law comes in very handy. What does the Gauss law tell us? It says that if the mass is spherically symmetrical, well, simply symmetrical, and you are inside the planet, if you're inside the planet, then you can mentally split the planet into 2 parts. Okay. So this part of the planet which is closer to the center than you are, and part of the planet that is further away from the center than you are. And the Gauss's law says that the field from the outside part is 0. The force from the outside part is 0 because it cancels out. Because what it does, like this part of the planet pushes you up, but the whole other part of the planet pulls you down, and these forces are balanced. So if you are inside the planet, it's equivalent to you standing on a smaller planet of a smaller radius. So the force that you would feel would be the same as if you were standing on a smaller planet. Does this make sense? 1, it does not make any sense, and 10, it makes perfect sense. In the chat, please. Okay. So if you dig a very deep hole and you go to the bottom of that hole, the gravity you would experience is equivalent to you standing on a smaller planet of radius r. And overall, you are standing on a planet you're standing on the Earth. It's radius r capital. Okay. Now let's find the gravity, because now we need to calculate the mass of this smaller planet. And we know that the mass, let's call it m star. Why not? Capital M. Okay, masses of big objects are usually capital M. There's no rule for that, but we just like it this way. Mass is equal to density times volume. And density times the volume of a sphere is 4/3 pi r cubed. Okay, so the force you experience, force is equal to your mass, or G, mass of the planet, multiplied by mass of you divided by r squared. And then you plug that in, small m over r squared multiplied by mass, which is density 4/3 pi r cubed, and magic happens, r squared cancels. And what you have is a very interesting phenomenon. So F is equal to 4gm pi divided by 3 gm rho, I forgot rho, multiplied by r. And if you look at this expression, you will see that, well, this is a constant times r. This is a constant times r. So basically what I'm saying is that force is proportional to r. Gravity is force divided by mass. So it's 4g pi 4g pi rho over 3 times r. So gravity is also proportional. Gravity is also proportional to r. And obviously at the surface of the planet, gravity is the same. So what's happening here? So gravity is proportional. So bam. Gravity is proportional to r. And all we need is just to find the gravity on the surface. But we know the gravity on the surface. The gravity on the surface is g. And that's it. That's the graph. Of the surface is g. Okay. Well, because it can't suddenly change. So at this point, at point r, they have to be the same. No, if density varies, because the density at the center of the planet, so if density varies, rho would not just be a constant. It would depend on R. So you would have a slight curve. So with a higher density towards the center, which is the case, we would have like this. The graph would be slightly curved. Okay, because then because density. Now, now what about the potential? The potential potential is the work that you do potential. So potential energy, and you will see that in the assignment. We have the expression V is equal to minus G, mass of the planet, mass of the object, divided by R, where R is the distance. And the potential in very similar to, because you have force and gravity, which is force divided by mass. You have gravitational potential energy, GPE, gravitational potential energy, and the potential, sorry, U is the potential. So V is GPE, is GPE divided by mass. So the potential is U equals minus GM over R. So potential is potential energy per unit mass. So don't be afraid of the word potential. Potential is just potential energy per mass. Just the way that electric potential is the energy per unit charge. Right. So potential, and we know that we can draw the potential outside the planet, because we all know this graph. This is outside the planet, of course. And that's not how you do it, because it's negative. Potential is negative. So at R, where R is the radius of the planet, it's some value, which we will need to figure out. Well, it's actually quite simple. It's minus GM over R capital, where R is the radius of the planet, of the Earth in this particular case. And then it goes like this. This is the distance, and this is U of R. Okay. So in a way, the potential increases, and now when R when R is infinity, the potential is 0, which makes perfect sense. The energy is 0. The potential energy at infinity is 0, which is true. Okay. So what happens inside the planet? Well, inside the planet, you have to use the same expression. So you are you can think as if you're on the surface of a smaller planet, and you are r meters away from the center, and you can find the mass. So u just a second. Okay. Okay, won't try it anyways. It's minus g divided by r multiplied by m, and mass is 4/3 pi r cubed times rho. And like this, r squared. So it should be now. I really don't like the fact that they say that the gravitational potential at the center is 0, effectively, because that's what this is what this equation says. Um, Sorry. Well, yeah, it looks like it is true. So if you imagine yourself in the middle of the planet, and that's the only force acting, you're stationary, and you have no gravitational potential energy. Yeah, that doesn't make any sense. All right, let me let me think about this for a bit. So I am struggling to figure this out. Sorry. Yes, we can do that. We can use g. We can use the fact that g is du dt. In my notation, it's dt. So multiply this g dt du. Okay. And we integrate that. So, and because g is, oh, sorry, y dt, g d dr, dv dr, sorry, dv dr. And we know that g is 4g pi rho over 3r dr. And we integrate that, r from 0 to r, and u from well, u in the center to u on the surface. U on the surface. Okay. So u on the surface minus u on the center is equal to 4g pi rho over 3 r squared over 2. Oh, the minus. Because minus, which is quadratic relationship over 6. And at the surface, yeah, it does seem it's going to be like this, but okay, I am sorry. Yeah, sorry. No, it's not like this. The gravitational potential looks like this. It's a quadratic curve, but it's a quadratic curve like this. And this should be, yeah, that makes perfect sense. Minus 3 over 2 gm over r. Okay, the proof of that is it's actually in the assignment, right? So yes, sorry about that. Minute of madness. Okay, so the draw a graph of GR and UR for a hollow planet of radius 3r with a central cavity of radius r. So what we have is a planet of radius 3r, and there's a cavity of radius r inside. And we need to do a similar thing. Let's keep it simple. Just not do the U. Okay. Okay. Well, we'll see how it goes. Let's see how it goes. All right. So the radius, and this is going to be the gravitational field G of R. Now outside, there's nothing. There's no surprises. So outside, so this is 1, 2, 3r, 3r, and outside is going to behave just like a simple planet. Okay. Let's figure out the gravitational field. So the gravitational field, as we know, is equal to gm over r squared, and the mass, well, the mass, so g over r squared, the mass is 4/3 pi 3r squared times the density minus 4/3 minus the cavity pi r squared rho. So this is 9, so it's going to be 8. It's going to be 8g over r squared multiplied by 4/3 pi r squared. Okay, so the 8 comes because it's 9 minus 1. That's where the 8 comes from. Hope that makes sense. And so if the planet was so the gravitational field is 8/9 of what it be without the hollow part. That makes sense. So gravity. So if there was no cavity, with no cavity, gravitational field at the surface, the gravitational field is G0. Yeah, G0 is the gravity on the surface if there was no cavity, and with a cavity, because the mass is 8/9 of what it would be without the cavity. So gravity is 8/9. 8/9 G0. 8/9 G0. Okay. So, all right. So that's what's happening inside. Okay. Now, let's say you are standing here. And there are two things. So this part of the planet is pulling you down, except the middle bit. So that's going to be. So if you're standing at x, and x is r meters away from the center. Standing at x. I'll copy that. Standing at x. At x. So the gravity is the same, G over r squared. This is r multiplied by the mass. Now the mass is going to be the mass of the whole thing minus the mass of the middle bit. So it's going to be 4/3 pi r small cubed times the density minus 4/3 pi r capital cubed times the density. That's the gravitational field. So it's a cubic relationship, cubic minus something. And one more thing that you really need to understand, that if you're inside a cavity, the gravitational field inside is 0. Just like the electric field inside a conductor is 0, the same way the gravity inside a hollow is 0. And this is a cubic relationship. So when it's r, it's 0 until r, because you're inside a hollow cavity. And then it's a cubic relationship. So it must be, is it a positive or a negative one? It's a positive cubic relationship minus. So it's going to be like this, curved. It's quite steep, like this. Okay, so you got a similar task. So gravity is this. You got a very similar problem in your paper. What about the the potential? Well, the potential inside, do the same mistake again. The potential inside a hollow sphere is constant. Inside the cavity is constant. So if you have a well, okay, let me do this first. And this is R. So until 1, 2, 3 R, until 1, 2, 3 R, it's going to go like this. The same as if, so it's proportional to -1 over R. And then it's a quadratic. The same logic applies, and then it is constant. So inside the cavity, it's a constant relationship. Okay. I don't want to. Sorry, it's not this one. So like this, and then a constant line because that's R. So I won't go into the maths here. You can do it. You can do it on your own. So inside a thin shell, sorry, inside a cavity, inside a cavity, inside a cavity, G is 0, and the potential is constant. This is a very important thing. So if you have a planet which is a thin shell, so a thin shell, imagine the Earth was empty inside, just a thin crust and empty inside. The graphs would look like this. So it's a thin shell planet. Gravitational field and R would look like this. So 0 until the radius of the planet, R, and then like this. Okay. And if we were talking about the gravitational potential, so at R, this is R, this is potential. It's like this, and then constant inside. Potential. This is minus Gm over R, and this is Gm over R squared, radius squared. Right. Oh, G is dV over dr. That is a result you can use. Even if you're not at the center, yes, G is 0 everywhere in the cavity, absolutely. So just going beneath the surface. The logic behind this is that if you have an empty shell, and if you're standing, let's say you're standing here, you're being pulled this way. Okay, you're standing here, and this part of the mass is pulling you that way. is pulling you up. But this mass is pulling you the opposite way. Okay. And because the distance, let's say this distance is r, and this distance is 2r, but the air, if this area is a, this area is 4a. So you have the force is going to be proportional to the area over r squared, over the distance. And you double, if you quadruple the area and double the distance, it's the same force. Basically, you're being pulled in two different directions by this chunk and this by this chunk. And because this chunk is twice as far but 4 times as large, it produces the same force as this chunk. And this, you can do this for any two equal any two pairs of surfaces, and or you can do it by integration. You can prove that the field inside is 0. And this is a wonderful result. And you have the same result for an electric field. The electric field inside a hollow charged shell is 0. Okay. Problem 3. Imagine a system of 4 stars of mass m forming a square of side length L. Find the period of rotation of such a system. So you have 4 stars of equal mass. 1, 2, 3, 4. And they are going round and round. They're going round and round and round. As if forming an invisible square of side length L. Side length L. Okay, so let's look at mass number 1. Looking at mass number 1, we see that there are 3 forces. F1, F2, and F3. Which one is going to be the largest? Well, which one is going to be the largest or the smallest force? I've given you a hint. The smallest is F3, yes, because the distance is the largest. Okay, it's actually going to be 2 times smaller. Okay, so F1 is G M M, because they're equal mass, divided by L squared. And F2 is also that. And F3 is going to be G M M divided by, well, L squared. This is square root of 2L. So it's going to be 2L squared. 2L squared. So in other words, F3 is a half F1. Okay. But then we need to find the resultant force, because we know that the star is moving in circles, and the radius of that circle is L over 2. So circular motion. Circular motion. The force is equal to m omega squared r, which is, and the r is L over 2. L over 2. M L over 2. And we need to find the force. And the force is, well, it's this force and the sum of these 2 forces. And the sum of these 2 forces is square root of 2 times that force, if that makes sense. because F1 and F2, the resultant force is going to be square root of 2 F1. Isn't the radius root 2 over 2? Oh, yes, thank you. So L divided by square root of 2. Sorry. Yes, L divided by square root of 2. So the force, so the resultant force is equal to F, the resultant of these two, so square root of 2F1, square root of 2F1, plus a half F1. And that is equal to M omega squared L over square root of 2. And all we need is to plug things in. Square root of 2 plus 1 over 2 times F1, which is G M M divided by L squared equals M omega squared L over square root 2. So we need omega, so M cancels, omega squared.
You included F2.
Sorry?
You included F2, the force from F2.
So look, the modulus of F1 plus F2 is equal to the square root of 2 F1.
Okay, yeah, I see. Thanks.
Yep.
Yeah.
So that's why, because they form a square. So F1 plus F2 is square root of 2F1. Okay. For simplicity, let's call this F, and this no, let's not do that. Sorry, that's gonna just make it more confusing. Right, so omega squared can be simplified. So we multiply everything by square root of 2. It's going to be 2 plus square root of 2 over 2 times G M divided by L cubed. Can we make it prettier? Perhaps as 4, well, 4 plus square root of 2 over 2 G M over L cubed. And that's the frequency, that's the angular speed, and then you can work out the frequency, of course. So it's the time period. So time period is 2 pi divided by omega. So it's just doing some maths here. So you take the square root of that and plug it into here. So I'm gonna keep this to you. But yeah, I mean, interestingly, like, you have a very similar problem. You have a similar problem with 2 stars in the assignment, and you have a very similar problem with 3 stars. 3 stars. So when you look at one of the stars, you just look at the 2 forces acting on that star, and that's your resultant force. And then you do resultant force is equal to M omega squared R, just the circular motion equation, and that's it. That's all you need to do. So it's a much easier problem than it looks. So I'll just delete that because just not to get you confused, in case you were looking through the notes. How much do we have? 3 more questions. Oh, so 4 more questions. Okay. Yeah, I think we can manage. Now, problem 4. What I'm trying to do here is I'm trying to show you, like, how did people know the mass of the Earth and the mass of the moon and the mass of the sun, but just by looking, because obviously it's very difficult to find such things. This is one of the ways. So knowing that in a year the moon does 13 full rotations, and that the distance to the moon is 390 times smaller than to the sun. So things that can be deduced using telescopes. Find the ratio of the masses of the Earth and the Sun. So basically we have two systems. We have two systems. So we have the Sun, the Earth going around the Sun. And we have the Earth, and we have the Moon going around the Earth. Well, various methods are used. Yeah, like depends on what you're looking at. How do we find the distance? How did you find the distance to the moon? I can't tell you at the from the top of my head, but there are lots of techniques that you could use. No, I'm curious. I'll need to look it up. Sorry about that. Okay, so we have two systems: the Earth going around the Sun and Moon going around the Earth. And okay, so the force is equal to G mass of the Sun, mass of the Earth, divided by telescopes into different places and trig. It might work for the moon. Yeah, but if you know the radius of the moon, it's easy to calculate the distance, and vice versa. If you know the distance, it's easy to calculate the radius. And so this is, let's call this distance r, big R, and let's call this small r. So r squared. And we know that the mass of Earth multiplied by, because this is circular motion, we can still use circular motion. So it's omega squared r is equal to G m Earth m Sun divided by r squared. Me cancels, and we get, and omega squared is 2 pi, so it's 4 pi squared divided by t squared equals to G ms over r cubed. And this is Kepler's second law, actually. And Kepler's second law says that the square of the period is proportional to the radius cubed. It's Kepler's third law. This is a very important law. Unfortunately, we didn't have space to add this. I really wanted to add this into the assignment, but we just thought it's going to be too huge to include that. Because these are constants. Okay, so in a similar way, we can write 4 pi squared divided by this t t1, let's call it t1, t2 squared is going to be g mass of Earth divided by r cubed. So we need to find the ratio of the masses of the Earth and the Sun, or the Sun and the Earth. So mass of the Sun divided by mass of the Earth. Mass of the Sun divided by mass of the Earth. So the ratio from here, mass of the Sun is equal to r cubed 4 pi squared divided by g t1 squared. So r cubed 4 pi squared divided by g t1 squared times. So then mass of Earth, so we do r small cubed 4 pi squared divided by g t2 squared. 4 pi squared cancels, g cancels, and we are left with mass of the Sun by mass of the Earth is equal to r divided by r cubed multiplied by t2 divided by t1 squared. So radius, so we know that the radius of the orbit is 390 times, so it's 390 squared, cubed, sorry, multiplied by t2 over t1. So t2 is 13 times, 13 times, which one is bigger? So period is 13. So it's 1 over 13. 1 over 13 squared. Does that work? 390. 390 squared divided by 13 squared. 390 cubed, sorry. Cubed. 351,000. 351,000 times. Let's see. 351,000 times 6 times 10 to the 24. Yeah, brilliant. That's really cool. So basically by just knowing the distances, by how many times the distance is bigger and how long it takes, you figure out the ratio of masses. You know that the Sun is 351,000 times heavier than the Earth. So this is a nice piece of physics here. I wouldn't say it's because this is very close to physics and very far from math. It's just ratios, and you can see the Kepler's second law seeping through the ratio of masses. So it's r cubed and t squared. So r cubed, t squared. And we know, we have made the measurements. We know that the mass of the Earth is 6 times 10 to the 24 kilograms. It's a very useful result to remember. And the mass of the Sun is 2 times 10 to the 30 kilograms. And you can see that if you multiply this by this, you get this. There is a YouTube channel. Yes, just the COMPOS YouTube channel. I'm not sure you can find it, but try looking for it. There's definitely another channel called COMPOS. But yeah. The link is on our web page. If you go to our main web page, you'll find a link to all the YouTube videos. Okay, problem 5. Another thing. So we know the radius of the sun. You know the distance to the sun. You know the length of a year, which is 1 year. From only these data, find the average density of the sun. So you would think like, oh, the sun must be quite heavy. Like the sun is 351,000 times heavier than the Earth, so it must be quite dense, or maybe not. Question is, well, is it denser than things you know? Can anyone say the density of water from the top of their head? Density of water, the easiest one. 1,000, yes, well done. Density of gold. Gold. Density of air. More than 1,000, Harrier. Thank you. Density of gold. It's 19,800, I believe. 19,800 or 17,800. Density of gold. Density of gold. It's one of the most dense materials. 19.3. So 19,300. Okay, I was close. 19,300. Yeah, one of the heaviest metals. Okay. So yeah, the density of air. Another thing you should know, it's about 1 kilogram. 1 kilogram per cubic meter. Quite a useful thing to remember. Density of water you should know. Density of gold, like who cares? You can always look it up. Okay. Kilograms per cubic meter. Right. So where does the density of the sun? So what we are trying to compare density of the sun. What do you reckon? What's your guess? Let's get some guesses. What's the density of the sun? Make a guess without looking, obviously. 50. Okay. So good. 50. 3. Be less than same as air. So 1. 30,000. Okay. Let's do the calculation. Let's see what's closer between 1. So denser than water, yeah? Mads, you're saying it's between 1 and 2,000. Denser than water. So you think the sun is denser than water, but less dense than sand. Okay. Right. The density of aluminium is another one. Easy to remember. 2,700. Yeah, because it's a light metal. So aluminium 2,700 and gold is 19,300. So it's way more heavier. Anyways, let's do this problem. So the radius of the sun, we don't really care about this one. The distance to the sun is this. So this is the sun. And this is the Earth. And we already have this result, and I don't want to do it again. So we have this. Mass of the sun, and we need the radius. So let's call it small r, and the distance to the sun is big R. The length is 1 year. Then we need to find the density. Density of the sun is mass of the sun divided by the volume of the sun. And the mass of the sun is r cubed 4 pi squared divided by gt1 squared and divided by the volume, which is 4/3 pi r small cubed. It's very important because it's the radius. This is the radius of the orbit, and this is the radius of the sun. Is there anything we don't know? No, we know everything. So just make some cancellations. 4 pi cancels. So we get r cubed 3 divided by gravitational constant T1 squared r cubed. Okay. So 3 multiplied by 1.5 times 10 to the 8 cubed. So this looks like it's going to be massive, right? Because we have 1.5 times 10 to the 8 cubed. Yeah, solar mass. Gravity is 6.11 times 10 to the minus 11. So making the whole thing even more massive, multiplied by the time period. So 1 year squared. So 1 year is 86,400. That's seconds in a day times 365 days. Technically it's 355.25, but we are allowed. This is already 3 significant figures. You don't need 5 significant figures. Times r cubed, which is 60. Well, as long as we do the same in kilometers, it doesn't really matter. 696,000 cubed. And this is squared. I got a feeling that this is going to be a massive number, which it shouldn't be. Times 1.5 times 10 to the 8 cubed. Why did I say 6.11? Gravitational constant. 6.37. 6.67. 6.67. Very sorry. My brain stops working sometimes. 6.67 times 10 to the minus 1. 6.67 10 to the minus 11 times 86,400 times 365 squared times 696,000 cubed. $452. Which does not seem right. Oh yes, pi, thank you. Divided by pi times pi. Which is approximately 1422. Oh yeah, it is. Average density of the sun is in fact that. I was that is very surprising to me. Like honestly, it's 141, and yeah, it's just more dense than water, and kilograms per cubic meter. So well done. Some of you got it. You're right on the money. Mads, well done, and Isa, well done, and Josh and Binny, really close. Well done. It's just slightly denser than water. And I am honestly surprised. My guess would be around 100. I would think, because and this is because it's it's really not uniform density. The core of the sun is incredibly dense, but the outside of the sun is not. The outside part of the sun is really not dense. If you were to grab from this goes to the surface, it's just a gas. Two or three significant figures is normal, right? We are not. We are doing approximations pretty much everywhere. You're given two significant figures here. The distance in the distance. That means your answer cannot be more than two significant figures. So yes. I'm sorry for that. Okay. At COMPOS, we really don't care much about significant figures. Okay, A levels is important. Yes, we try to be scientific. We're I mean, we will never punish you for the wrong significant figures. We might say, please use three significant figures, but that's not the point. What we're trying to do is we're trying to teach you to problem solve, because these problems they're harder than school problems, and what makes them harder is because every question is it's not just applying your knowledge. Is you need to think about it. What you do, you need to make assumptions. Sometimes you need to build a model in your head, and all the problems are multi-stage. You don't have a problem where you just need to find the gravitational potential energy of a mass that which is lifted above the ground. We always make it more interesting. Okay, we have two things to do. Now, let's do problem 7 first. And now this problem comes from a book, and this book is called Physics is Fun. And I read it when I was about 13 years old, and that's what got me into physics in the first place. Okay, and they described this particular problem, so I just remembered it off the top of my head, and I decided to discuss this. And also, I read the book, the Jules Verne book, the From the Earth to the Moon, and in this book, the main heroes are shot from a cannon, and they go to the moon. Okay, they go to the moon. And in the book that I read, Physics is Fun. By the way, I have a copy, and I can share it with anyone that's interested. It's a fantastic book. I have a PDF, basically. I can share it with anyone. It's an old book, though. In general, from the Earth to the Moon, the capsule was shot from a 700-foot barrel, which seems like a lot. The maximum acceleration the human can handle is 9g. Okay, some trained people can handle 10 or 12 g's. To explain why shooting from a 700-foot barrel is not possible. Well, I'll try to be swift here. So, because in order to leave the Earth and travel to the moon, you need a minimum speed. You need a minimum speed, which is called the escape velocity. So let's say the barrel, the cannon is here. You shoot from the cannon. You shoot from the cannon, and it goes like this. You want to, sorry. Cannon shoots barrel and goes like this. So the minimum speed that you need is called the escape velocity. And this is calculated in the following way. When you go infinitely far, you want to have, so at infinity, you want your gravitational potential energy to be zero, and your kinetic energy to be zero. So your total energy is zero. Now, on the surface of the planet, you already know that your gravitational potential energy is, we are grown up, so we are not using mgh anymore. We're using minus g, mass of the planet, mass of the ball, of the cannonball, divided by radius of the planet. And your kinetic energy is 1/2 mv squared. So nothing's changed here, mv squared. So your total energy has to be equal to 1/2 mv squared minus gmm divided by r. And this has to be equal to 0. So the speed that you need from here, if you do the calculations, m cancels, is approximately 11.2 kilometers per second. 11.2 kilometers per second. This is called the escape velocity. Sorry, I've walked through this. Does everyone understand how I get v? Does everyone understand? So at infinity, so if you want to go to infinity, if you want to shoot yourself from a cannon to infinity, your total energy has to be 0. Do you understand this on a scale of 0 to 10, please? Your total energy is 0 on a scale of 1 to 10. And because we have conservation of energy, when you shoot yourself from a cannon, you also need 0 total energy. So total energy when you are starting is also 0. This is okay because the gravitational potential energy is negative. So your kinetic energy is positive, gravitational potential energy, the total energy is 0. In other words, your kinetic energy must equal to your gravitational potential energy with a negative, with the opposite sign. And if you do the calculations here, because you know the mass of you know the mass of the planet, you can look it up. You know the radius of the planet is 6,400. If you plug that in, you get 11.2 kilometers per second. That's the minimum speed required to leave Earth's gravity. And this is the speed you need to leave to go anywhere. You need to go to, if you want to go to Mars, you need that speed. If you want to go to, well, okay. Now, but the rest of the problem is simply a SUVAT problem, because you have a 700-foot barrel, which is 220 meters. So you have a barrel, and you have a cannonball, or a bullet with people inside. So in that book, there are people inside, astronauts or cannonauts. And it is accelerating, so you can assume a uniform acceleration. You can assume a uniform acceleration along the cannonball, along the cannon, and the distance is 220 meters. 20 meters, and your final speed must be 11.2 kilometers per that's your final speed. So just a simple suvat, and I won't even bother with. So it's just v squared minus u squared is equal to 2as. So v squared is 11,200 squared minus 0 squared equals 2 times acceleration times 220. And if you find the acceleration, is 11,200 squared divided by 440. 285,000 meters per second squared, which is approximately 28,500 Gs. Okay. What does that mean? That means that your whole body becomes 285,000 times heavier. Okay, so if you're wearing a watch which is 100 grams, it suddenly becomes 3 tons. Well, it certainly feels like 3 tons. You won't be squashed into a pancake by your hat or by your hair or whatever. Yeah, just people don't like acceleration. And I think Jeremy Clarkson once said, speed has never ever killed anyone. It's suddenly becoming stationary. That's what gets you. Acceleration is the thing that damages humans. So big acceleration is incompatible. So people can't survive large accelerations. And how long would the barrel be? How long do you need to make the barrel to stay within the 9G limit? Well, it's up to you. You can figure it out. It's a very simple suvat problem. So yeah, so I just really like this problem, and there's a lot of things to think about. A bottom line is, yeah, not very realistic to shoot from a cannon, unless the cannon is 17 miles long or something like that. Problem 6. The landing module of a lunar mission is launched from the surface of the moon to meet the orbital module, which is in a circular orbit 1,700 kilometers above the surface of the moon. What is the necessary initial velocity for the two modules to meet without speed corrections of the orbiting module? So there's lots of stuff. So the landing module. So let's just have a look. Like, I mean, look, when you encounter a problem and you have no idea what they're talking about, so let's go. So landing module, Apollo. Let's see what it is. Okay, so it's this thing. So what does it do? Is there a diagram? Trying to make sense of it. Well, it seems like there are two modules. There's the landing module, and then there's the orbiting module. Okay, and you can actually watch it. Right. And yeah, and the American Apollo program and the Soviet moon program, they had very similar technology. Yeah, so there's a orbital module and a landing module. So the orbital module maintains orbit around the moon, and it has fuel reserves in order to get back to the Earth. So you have the moon, and then there is a orbiting module. The orbiting module, which is this one. So it's And then there's a landing module. So basically the landing module, which is here. Now, just the top of the landing module, so this part stays on the surface of the moon. You can actually watch the video, and this goes on top. So this is catapulted, basically. It's catapulted up. It's catapulted up, and then what happens is when it meets the orbiting module, they link together, and then they fly back to Earth. Okay. So what does it mean? So it's in a circular orbit, 1700 kilometers above the surface of the moon. Oh yes, the moon, the radius of the moon, is also 1700 kilometers. So it's the same as the radius of the moon. Okay, so this is r, and this is 2r. So it's double the radius. And the question is, how fast do we need to launch it? So what is the launch speed in order to reach the orbit? And what does it mean without speed corrections of the orbiting module? What does that mean? So we launch the capsule, it reaches orbit, and what does it mean without speed corrections? They need to link, yeah. So when the landing module goes up and the orbiting module is on top, when they meet, they have to have the same velocity. If they have the same velocity, they can link. If one is traveling 100 meters per second, the other one is 150, they won't crash. Yeah. So if this one is going 100 meters per second, this one also, by the time it reaches the top, has to have the same speed. So let's call this initial velocity u, and this is traveling at velocity v. Okay, so by the time it reaches the top, it has to travel with the same velocity v. All right, so this is a conservation of energy problem. So on this surface, we have GPE. GPE is equal to minus GMM, where this is the mass of the moon, divided by R. And the kinetic energy is equal to 1/2 mu squared in orbit. When it reaches orbit, this is we're talking about the energy of the landing module. We don't care about the energy of that one. In orbit, gravitational potential energy is equal to minus GMM over 2R. So it has half the potential energy, and kinetic energy has to be 1/2 mv squared. And they have to be equal. Okay. They have to be equal, and so this plus this, so 1/2 mu squared minus GMM divided by R has to equal to 1/2 mv squared minus GMM over 2R. Let's make some, so M cancels. Okay. M cancels. Multiply everything by 2, I'm guessing. So u squared minus v squared is equal to plus is going to be 2 minus 2 times 2, so GM over R. Okay, just double check that I'm correct. I multiplied by 2. I combine these two, so it's positive. So that is 2 minus 1, so 1. Yeah, GM over R. So that should be true. But if we analyze this, we still have 2 unknowns, U and V, and we need to find U. Okay. Now let's look at the orbital module, because it's going in a circle. So the orbital module, we know that mv squared over 2r, the centripetal force, must equal to g m, this is m1, the mass of the moon divided by 4r squared. So m cancels. We have v squared is equal to, so 2 r, so it's g m over 2r. Oh, nice. Gm over 2r, so that's v squared. That's the final speed. Yeah, exactly. So from here, we have u squared minus gm over 2r equals gm over r. So u squared is equal to 3 over 2 gm over r. Oh, essentially it's 3v. It's triple the speed. And but yeah, 3v squared. Sorry, yeah. So not triple the speed. It's 3v squared. So u is square root of 3v, where v can be calculated. V can be calculated from here, if you know the mass of the moon. Usually you are also given the gravity on the surface of the moon. Sorry, yeah, we are supposed to know the gravity on the surface of the moon. Gravity on the surface of the moon is 1.6 meters per second squared. And we know that the gravity on the surface of a planet, gravity on the surface of the planet is equal to gm over r squared. So in other words, gm over r. So from here, u squared is equal to 3 over 2 g m over r, gm over r, over r squared times r. So it's 3 over 2 gr. So u is equal to square root of 3 over 2 times g, which is 1.6, times r, which is 1,700,000 meters. And if you do that, you get square root of 1.5 times 1.6 times 1,700,000. 2019. Oh, 2000 meters per second, which is reasonable for spaceships. This is the speed that you need in order to match. But I mean, look, the physics is going on here. The physics is going on here. It's a conservation of energy, really important. Make sure you understand this very well. And this expression is also very, very useful. Gravitational field on the surface of a planet is gm over r squared. All right, I hope I didn't bore you to death, and yes, enjoy doing the assignment. I have 3 minutes if you have any questions. Otherwise, see you.
Can I ask a quick question?
Yeah.
So, you know how some formulae have a negative in front of them and some don't. Like in the assignment, it says F equals GMM over R squared, but in my A-level regular textbook, it has a minus in front of it, and then I get confused because different formulae have just use different conventions, and I don't really get it.
Different formulae. True, they use different conventions, but
like which ones do you have? Like gravitational potential energy, you have a minus in front of it, and so does the textbook. Does that mean that it has to have a minus in front of it? And if so, why? Why does it have a minus in front of it?
because potential energy is negative.
But why is it negative?
Well, because we agreed to say that gravitational potential at infinity is 0.
Okay,
right?
but still, but why is it negative though?
Well, imagine if it wasn't negative. Imagine if it was positive. Yeah?
Yeah.
Let's say you are on the surface of a planet and you have 10 joules of gravitational potential energy.
Mm-hmm.
Now, and you have, let's say, 10 joules of kinetic energy. Right?
Yeah.
If you go to infinity, you have the energy is conserved. You go to infinity, and now you have your total energy is 20 joules, right?
Oh.
So that means you have 20 joules. I mean, and because potential energy is 0, you have 20 joules of kinetic energy. So you're speeding away from the planet, which doesn't make any sense.
Okay. Yeah.
So it has to be like that, because at infinity your total energy is 0. That means your kinetic energy is always positive because it's a square, and that means that potential energy has to be negative. Okay, because the potential energy increases as you go away. Yes, that's the key thing. Potential energy increases as you go further away from the planet, correct?
Yeah.
But at infinity, it is 0. So it's increasing, getting closer and closer to 0.
Okay. Yeah.
Yeah, so it has to be negative.
Oh, okay. Yeah, that makes sense. Yeah.
Right. Okay. Okay, physics is fun. Yes, I found the book, and I'll post it on the one. And no, you shouldn't be concerned. Noah, is it? Have you submitted into Google Classroom? Have you submitted to Google Classroom? Yeah. So if you submit it to Google Classroom, it won't be marked. So don't be concerned unless you have a note saying that we cannot read it. Do you remember which group are you in? Can you let me know which group are you in? I'll just double check. No, the group is a G1, G01, G02, G03, G04, G01. Are you using your name in it? Are you using your name? What's your name in Google Classroom? Oh. No, it's marked. You got just under 50%. You got 21. Oh no, you got more than. You got 21 out of 45. Yeah, that's for physics. 21 out of 45. So it's just under 50%. And maths. 60 out of 65. Yeah. So yes. I'll send you a private message. Okay. Based on the results. Okay. Right. We won't be assigning tutors. We won't be assigning tutors soon. Probably this week. All right. All right. See you, everyone.